The solid shaft and tube shown are subjected to a shear force of 4 kilonewtons. Determine the shear stress acting over the diameter of each cross-section. So now we've got a pair of tubes, basically, one solid, one with a hole in it. And so I have this 4 kilonewtons of vertical shear stress acting on it. So I'm going to find the shear stress acting over the diameter. And if you're looking at over the diameter, well, that's definitely talking about the horizontal shear stress. So our equation for horizontal shear stress is T, sometimes you'll see it TH or T horizontal, is VQ over IT. So we have our V. So now we have to calculate out everything else. So we'll do these kind of side by side, since we'll be looking up similar things. And so let's just run through them. So the first thing that we need to do is calculate out the moment of inertia. And the moment of inertia is a property of the entire cross-section. So we'll start with we'll use IS for solid, and we'll use IT for the tube. So it's a circular cross-section. If I look that up, the equation for a circular cross-section is 1 over 4 pi c to the 4th, where c is the radius. And so for the solid one, it's easy. Just 1/4 times, we're going to convert this over to meters. I'm going to raise that to the 4th, and that's all there is to it, except there's a pi in there. I forgot that, so pi over 4. We calculate that out, and that's going to be 4.909 times 10 to the negative 6 meters to the 4th. Okay, and so now we've got the eye of the tube. Now, don't really have a equation for the moment of inertia of the tube, but we do have this property of superposition. We'll take the moment of inertia of the entire thing and subtract from that the moment of inertia of the cutout. So we can go pi over 4, c to the 4th, and that would be our outside, minus pi over 4, c to the 4th of the inside radius. Now, I already know what pi over 4c, the outside, is. That's 4.909 times 10 to the negative 6 meters to the 4th. So now I'll subtract from that pi over 4. Our inside radius is 20 millimeters, so 0.2 meters. Raise that to the 4th. And so I'll get a moment of inertia of my tube of 4.783 times 10 to the negative 6 meters to the 4th. Okay, so now our eyes are taken care of. And now what we need to worry about is we need to worry about Q. So remember, Q is the area that is the area times the moment of inertia. I'm sorry. It is kind of like the moment of inertia. It is the area above the cut times the location of the centroid of the cut. So Q of S is going to be y bar prime a prime. Now, this one's a little bit easier because we are doing a right at the diameter, so we've got a full semicircle above where we're locating our y value. And so what we're going to have to do is if I look at that, and I'll draw it up here, I need to figure out what the y bar of a semicircle is. So I looked that up in the book. And one of the books will tell me 4c over 3 pi. And then I have to multiply it by the area. So the area above the cut is going to be that entire circle. And so we know areas are pi r squared. And so we're using c for the r in this problem. And it's half the circle, so we'll just divide that by 2. And then we can plug everything in. 4 times 0.05 meters squared divided by 3 pi. Multiply that by pi over 2 times 0. I'm sorry, that's not a square there. 0.5 meters square. And I plug all that together, and I'm going to get a Q. So this is my A prime. This is y prime bar. I'm going to get a Q of 83.33 times 10 to the negative 6 meters cubed. Okay, how do we calculate this for the bigger one? Well, this is where we're going to use superposition. So to get this guy here, I'm going to take both my area and my y-bar location, and I'm going to subtract out the little portion to give me this half circle tube. Okay, so Q of the tube is going to be Q of the solid minus the cutout. And so what's the cutout going to be? Well, the cutout's going to be same thing that we've done here, because once again, the cutout's still a semicircle. So 4c inside divided by 3 pi times pi over 2 ci squared. So we've already got the Q of the outside one, which is 83.33 e to the negative 6 meters cubed. And we'll subtract from that 4 times 0.02 meter divided by 3 pi times pi over 2 0.02 meter squared. And so that will give us a Q of the tube to be 78 times 10 to the negative 6 meters cubed. So these are the numbers that we're going to need for our equation. Now the thing to remember with Q is it's always, we're just looking at the shape above where we're cutting. Q is always probably one of the more difficult things that we ask you to solve for conceptually. Students have an issue with that, but just think about it. Draw your line where you're looking for the horizontal shear stress, and then you're just calculating everything over that line. Okay, so one thing I do want to talk about next is thickness. And so thickness is the thickness of the cut. So like this guy right here, the thickness is going to be that. It's going to be over the entire diameter. So the thickness of the solid is going to be 0.05 meters, because this is where the shear stress is acting. Now the thickness of the tube is going to be a little bit different, because you've got material here, you've got material there, but then you have air in the middle. You can't have horizontal shear stress in air. You can only have it in the actual material itself. So if I look at this, and actually, I'm sorry, this is times 2, because it's 50 millimeters radius, it goes across 100 millimeters. So what I've got here is 50 millimeters minus 20 millimeters of air. So I have 30 millimeters of material on the one side multiplied by 2. 100 millimeters of thickness for the solid bar because it's all material. 60 millimeters of thickness on the hollow one because I've only got materials at the two ends. Once again, this is another place people will get tripped up a little bit. So let's go to the big payoff then. Via the solid, the horizontal shear stress of the solid is VQIT. I'm just going to plug in all the numbers that we've got. We've got that 4,000 newtons. We've got a Q of 83.33 times 10 to the negative 6 meters cubed. Our moment of inertia is 4.909 times 10 to the negative 6 meters to the fourth times 0.1 meters is our thickness. So as I look at the units, I've got meters to the fifth on the bottom. I've got meters cubed on top. That'll cancel out and leave me meters squared. So I'm going to have newtons per meter squared, which is definitely a unit of stress. So that's a good thing for us. So 679 kilopascals, or 679,000 Newton meters squared. So that's how much shear stress, the horizontal shear stress we have right at the middle of our solid bar. Let's look at the shear stress of our tube. Same equation, BQ over IT. We have the exact same vertical shear force. We have different Q, I, and T's. Okay, so we'll just plug in our different Q, I, and T's. So our Q is 78 times 10 to the negative 6 meters cubed. We've got our 4.783 times 10 to the negative 6 meters to the fourth. And we have our 0.06 meters. We plug all those in. Once again, newtons, got meters to the fifth on the bottom, meters cubed on top. That's going to leave us newtons per meter squared. 1.09 times 10 to the sixth, or 1.09 megapascals. So a lot more horizontal shear stress in the tube. Why is that? Well, it's over a lesser area. It's going to drive things up. Even though the I and the Q are a little bit smaller, the thickness of this is really driving that shear stress up. We're about, 80% higher it looks like. And so this is an example of how we calculate out horizontal shear stress.